wouldn't say that. I checked everyone and I was like, hey, we got that shredded
Do you start? Down?
I gotta go this way. I wrote down the first two columns, I didn't make sense. My first two pieces of paper. Yeah, I didn't know that was a problem. Like that? It's literally Excel work and then underneath two fucking positions. Thank not.
Alright. Good morning, everyone. How are you? Very good. You like today? No? You get a gift or anything? Alright, first we will start with homework. Homework 3? Homework 3, question 3. Who didn't look at it yet? Like, didn't even see it? Okay. Who can do it? Who can do it? Who did it? Just fine. What's your name, sir? Oh, you did it. Who did it? Just fine. Question 3. Question 3. Come here, please.
Oh no, I didn't do good. I didn't do good.
Who else did it? Just fine. Mr. Lee, did you do it? Just fine. You did it. Come here, please. Come here. Help me a little bit. Come help me a little bit. What's your name? Sean. Okay. Let's take a look at the problem statement. Question number 3. Sean. Okay, we have QG of 15 mmHg, Q out of 2500 mil. Okay. Mil, this is 75. Is it right, John?
Huh?
John or Sean?
Sean.
Sean. Okay. So we have all the operating pressure, operating temperature, specific gravity, SGI, L, actually SGL, specific gravity of liquid phase. Can you convert this to density? Can you? Yes, that's the formula. D sub M, 100 micron, retention time 2 minutes. Mil equal to that. A, what is the compressibility factor for this case of the gas phase? No problem, right? Clear enough? You can do it, it's really sharp. Compute the value of that coefficient. Use cosine in Excel to get C sub D. Get stuck, is it?
That's hard.
Or you can do it? Please explain, alright. C sub D, there are two methods. If it is, yes.
Yeah, when you use goal C, what value are you putting in?
Adjust C sub D until I didn't teach about how to use goal C. I teach how to do iterative method. You can do goal-seek. If you cannot use goal-seek, use iterative method. Yes.
But what value are we setting if we use goal seek?
If you want to use goal-seek, all right, we'll get that. Sean, how did you do it?
Okay, I think I did 3 iterations. I didn't use.
You did go iterate. It's fine. 3 iterations.
Fine, right? You did 3 iterations in class and you got a value, but how do you know when to stop?
When do we stop? I didn't talk about when do we stop either. How do we stop? Do we do 3 times and stop? We will have to do it until it repeats itself. That's when we stop. If it doesn't repeat itself, we don't stop. Okay? Is that clear? It's not like 3 times and done. No. If you do 3 times and done, it's acceptable, okay, but it's not going to be like very, very accurate. If you have chance, do it until it stops. Okay, how to calculate C sub D? Is this the same as the example in the class? Change it? We just change some number to trick you, right? Let's go back to the example in the class. Okay, C sub D calculation. Row L, do we have row L? Do we? Yes? Okay, we have row L. Row G, do we have it? No, we don't have it, but we have gamma. Do we have gamma? Gamma, how much is gamma? 0.7. Is that 0.6? Okay, that's a gamma of 0.6. Alright, what else? Pressure, temperature, compressibility factor. Do we have all those things? We have pressure 2000, temperature, we can do unit conversion to be Röntgen. Good? You can change it to Röntgen. Alright. So we can have rho G. Correct? What about compressibility factor? Read the chart, no problem with that. So we have all these things. And can we assume the initial value of C sub D equal to 0.34? Can we? That's no problem, right? Assume the initial value of C sub D equal to 0.34. Okay. If you don't want to use goal-seek, assume the initial value of C sub D of 0.34. And then, can we calculate V sub T? Terminal velocity. I have constant rho L minus rho G over rho G, all those numbers are known. D sub M, the value is given, right? And C sub D is 0.34, correct? So we get that number, that terminal velocity. Is it okay with you, sir? Sure. It looks still okay? Alright, then we redo the Reynolds number. Okay, I come up with my formula to do Reynolds number. This is a conversion factor that I put there. You should be able to get that too. Okay, so I put rho in there, and we what?
13048 is a conversion factor.
That is viscosity. On the top,
140
that is 3.71. That is rho G. That's rho G. Oh, okay. So the way that this formula works is based on is it fit? Okay, 140, that is micron changed to unit of meter, so that is meter already, right? But that this formula that have that conversion factor, it needs to have the input in the form of feet, not meter. So that's why I convert from meter to feet, okay? And that is diameter in the unit of feet. Do you have the diameter in the unit of, oh, that is velocity. Is it velocity? Or N66? That's velocity. So we can get the new value of Reynolds number, correct? Alex with the X, right? Is it clear up to this point, Alex? No. Let's go back. How about this number, Alex? Is it clear how we get that? Yes, that is terminal velocity, correct? Terminal velocity with the assumption that C sub D is 0.34, which is not correct. Okay, we assume that first. And then we plug the number in, value of density, and velocity, which is this one, and the diameter, to use this formula, the diameter has to be in the unit of feet. Okay, this formula that I made operate by have the input of diameter in the unit of feet. So I convert from micron to feet with that thing. Okay. Colin?
Yeah.
Good? This good?
Yeah.
Alright. And then this number should be more than 1. Okay? If it's less than 1, it doesn't do me anything. Because if it's laminar flow, we don't have to do the iteration. When it's more than 1, I get the new Reynolds number and I can calculate the new value of C sub D. Alex, you like that?
What?
Calculate the new value of C sub D. So first we recalculate Reynolds number. So do you have any question on this point for Reynolds number calculation? No problem. And then we can, this is a formula for C sub D. It has to be 24 over Reynolds number and 3 over square root of Reynolds number. So we plug the number in. So the formula comes from, I know that I going back, but okay, that's where I put it. The formula is drag coefficient. Here's the formula for drag coefficient. Slide 58. It's always 0.34 at the back. Okay. So I plug the value of new Reynolds number in there, I calculate the new value of C sub D. Good? And then repeat the process. Is that where you get stuck to repeat the process? I think you may get stuck on use code C if you try to use code C. Okay? The trick to use code C is on the test, we probably don't have this. Do you think you can do it on the test? I can just give you C sub D value on the test. Or we may not even have it. I know that I can do the iteration during the test, but I doubt if it's like really the test on this subject or the test on how to use calculator, so we may not have it. So in the homework statement, we have Reynolds number. We can calculate Reynolds number. Can we after we assume the value of C sub D equal to 0.34, then we can calculate terminal velocity. You like that idea, Alex? There's a formula to calculate velocity. Then we can calculate new value of Reynolds number. From the new value of Reynolds number, we plug it back in to get the new value of C sub D, right? And we keep doing that until it repeats itself. Okay? Then we stop. So who still gets stuck on this problem? Did I help you or it is not helping?
I just want the CD value.
How you have to do it? Is it helping? Yeah, you don't get stuck? For this part?
Are we gonna get the exact same numbers that are on the chart?
Could be. On the chart, let me look at the chart. We actually should. So there's a chart. Are you talking about Marty, are you talking about this chart? Yes?
No. the table, 4-1.
This is the chart for C sub D versus Reynolds number. If we have right Reynolds number, the value that we get should be similar to this. So Martin, what chart that you're talking about?
The table.
Table?
Table 4-1.
Is it table in homework? Okay, what do we do with this table in the homework? Okay, I think question B, you are fine with question B, right? Let's talk about question C. What would be the seam to seam length?
I don't know, what is it?
What would be the seam to seam length? And question B, for the given retention time, and the calculated parameter above, above. What would be the best suitable size of two-phase vertical separator? So retention time that we give is 2 minutes, right? And calculated parameter that we get from A, B, and C. So first we have to do question C. Question C and question D, it has to be done together. Is it together? Sean, how did you do question C and D?
Okay, so for CLSS, I picked the size and then checked it, picked the size and then checked it. If the diameter is less than 36, use one equation, and then greater than, use another. And then for D, you can say time equals 1440 times D divided by the flow rate, and then you can figure that out. You can back down all of that.
Do you like his explanation?
I'm not following.
You don't like his?
I don't understand it.
Okay, there could be, I'll repeat that. Okay, seam to seam length, you remember the problem statement that we have this? We have several seam to seam length, if you notice. You see that? Why do we have several of them? Because in that example, the way that Arnold Stewart did it is select several sides. So to calculate seam to seam length and other parameters, first we get CD value. You got that, no problem, okay? Once we have that, so in the homework, is it horizontal or vertical separator? Vertical separator, okay? Vertical separator, we have vertical separator equation. So in this is also, is this a vertical separator?
Yes.
This is also vertical separator. So when we do this, after C sub D, you see this equation, D square equation. This is gas capacity equation for vertical separator. You like that? You agree? Once you use this, look at capital T. Do you know the value? Yes, because we know temperature, right? We know temperature. Do we? Yes? What's your name? Another Sean? Yeah, you asked me a question, yeah?
Hunter.
Hunter. How many hunters? We have just one hunter, right? Another hunter. Okay, 2 hunter. Alright, T. Hunter, you get that. That is from the problem statement. Value of Z, we already looked from the chart. Q sub G, we have that. Pressure is the pressure inside the separator, we have that. Rho, we have that. C sub D, we just got it, right? dm is given. Then we can calculate D square, can we? Yes? Take the square root, we get diameter in inch. No problem with that, right? That is diameter in inch. Liquid capacity, okay, we put 2 minutes in, and then Q out, we have the value. So TR will be 2 minutes, then we can get D square H or something, okay? Now let's take a look at, so this is, that height will be liquid height in the separator. Seam to seam length, okay? Once we, so you will get some number, maybe not 21.9, But let's assume that you get some number, maybe 22, okay, 22. So when we calculate gas capacity, we get D of 22, okay. We put it back, so 22 will be minimum size of the vertical separator. This means from the available size, 22 diameter, it doesn't have 22 diameter, so this diameter, this is vertical, the settling volume high pressure, maybe this is horizontal, so that's horizontal, okay, horizontal, vertical high pressure. So we just want to get the size, okay? So this means this size is okay, but the size on the top is not okay. We don't use that. We have several options to use. 24, 24, 24, 30, 30, 30. The option that you may want to try, we try this option. Okay? 24, 30, 36, 42, 48. Can you try that? Sure, you can try that. You put it in seam-to-seam equation. Yes, sir.
Sorry to interrupt you, but that's for t equals 3 minutes, right?
Oh, okay. So let me draw this. Not that thing. So this is equal to 2 minutes. We kind of try several. Thank you to interrupt me. We try 24, 30, 36, and 42. Every diameter that we have, we can use liquid capacity equation to get H. Can we? Douglas, what's the question, sir?
42, not with the 1 minute retention time.
42. You can have several of them. Okay, the way that we select this number is come from this kind of table. When we see that, hey, look, this is vertical separator, this is the size that it works, and we pick a couple of them. So when the diameter from the gas capacity equation tells us that it's 22 inches, we can use anything that is larger than 22 inches. You agree? Yes, so we can use anything that is larger than 22 inches. But it's not every number that above 22 inches is available. It's available just 24, 30, 36, 42, 48, 54, 60. So we try those numbers. Okay? So in the homework statement, if you get something more than 22, the number that you may use to try may be less or maybe more. Got it? So we try each of them, and we have height calculation. You see that liquid height? That liquid height will come from this equation. So you put d square, we put 24 in there, we calculate h. We put 30 in there, we calculate h. We put any available number of diameter square, then we can calculate the height. Good? And then we have seam-to-seam length. Okay, there's an equation for seam-to-seam length for vertical separator. I'm going back, I'm sorry. Okay, this vertical separator, seam-to-seam length and slenderness ratio. Seam-to-seam length, we have two equations. So when we know h, we plug it in, and then we do the calculation, and then we get this number. If you want to know whether what you did is correct or not, make sure you can repeat what Arnold's George showed in the example first. Before even you do the homework, try to do the example in this. Once the example in this is correct, you just change the number and it will be correct. Okay? Yes, sir.
After getting D, why should I get different age? Because I can get different age, so the
Let's say your D equal to 22.
yes. So I'm
How do you know that the separator should be 24 inch? It could be 30 inch, it can be 36, inch. It could be 60 inch.
So how would I know?
We select that based on slenderness ratio.
But the edge also is going to change. My edge is.
Edge is going to change, of course. So we calculate every possible edge value.
Okay.
That's why this has to be done as a homework.
Okay.
So once we know D that is more than 22, we select every possible D, which is 24, 30. So every possible D, we calculate edge, the corresponding edge. Once we know edge, we calculate seam to seam length. Once we know seam to seam length, we calculate slenderness ratio. And we select the slenderness ratio that is between the recommended range. Okay. In this case, they do slenderness ratio between 3 to 4. So 3 to 4 is that one, for example. So the last two questions have to be done together. Okay, to select. So it's not like you select one first and then select another one next. We do everything all together, and at the end, we know what to select. So this table is just give you this is a copy and paste from the lecture slide. The number that you got on this column H, column L, and that will be different. Okay, this value will be different. What you may have it, and you don't even have that. So you will have something like this, or less or more. Okay, depending on what you got. Hunter, you like this? Is it still confusing?
I'm confused on, I can see how we can get the seam to seam length, but I'm confused on.
Seam to seam length, there are several seam to seam lengths.
Right, I get that.
Because there are several diameter, possible diameter. Seam to seam length, we have to calculate height first. And height come from what? Liquid capacity equation.
Yeah. So I get that, right? So now I'm just trying to figure out, how do we distinguish which one is better than the others?
Based on slenderness ratio.
Okay, but it doesn't give us anything here for figuring out which slenderness ratio we want to pick.
Okay, so we go, it doesn't give you anything. So we go with the slide, which is 3 to 4.
Okay,
So select the one that's between 3 to 4.
all right. It just says, given the information we have, pick one.
Yeah, the information that is given doesn't tell 3 to 4. So you select the one between 3 to 4. Good? No more questions? Try to meet with Arya, okay, or me if you have more questions. Let's go back to the separator. Alright, we talk about the theory part of how compressor work. When we do the compression, it gets hotter. The only way we can get the theoretical value is to make some assumption. Okay, we assume what? What do we assume? How do we get the theoretical value? We assume. Okay, next to Hunter, what's your name, sir?
Connor. Connor.
How do you spell it?
C-O-N-N-O-R. Connor.
C-O-N-N-O-R.
Yeah.
Okay. What do you do to get what is the assumption to get theoretical work required for the compression?
To get what?
Work required for the compression corner. What kind of assumption did we use? Do you remember last time that we used a chart? That chart, what is the assumption for that green line corner?
Constant enthalpy.
Constant edge enthalpy? Is that what you use?
Entropy.
Or S? So it's a entropy, so we do constant entropy. So one of the assumptions that we can use, thank you Conan, one of the assumptions that we use is constant entropy. Constant entropy means reversible process. Okay, constant because the level of chaotic level of the system doesn't change. So when it's constant S, it's reversible. So that's why in Ikoku, that's the name of textbook that we assume what is the theoretical horsepower consumed by blah 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 blah. Theoretical horsepower is based on constant S. You need to know that, okay? Not H. If you do constant H, that's wrong. Zach, what's going on? You still have more questions?
No, I figured it out.
You figured it out. Very good, very good, very good.
I know.
How about this? We have this chart. We use it to do theoretical horsepower. We assume constant S value or constant entropy. Okay. When we do constant entropy, we do the compression. We go from one pressure temperature to another pressure temperature. We move it up, right? So next to corner, what's your name? Colin? Where do we stop? We go up. Where do we stop? In the Euler diagram, we use constant S assumption or theoretical horsepower. We move the arrow up. Where do we stop? Or where do we stop?
That's the other pressure.
Temperature too? We don't know the temperature. We know the pressure that we want, but we don't know what is going to be the pressure that it gives. When we compress it, it will get hotter. We know the required pressure that we want to get, how much we want to get, but we never know how much will it get hotter. That number comes from the chart. So we stop at, so you see this is pressure of 200 line, pressure of 500 line, pressure of 1000, 1000, so that's pressure of 1000, pressure of 2000. In this particular problem, we have the set point that we want to compress, okay, 65 psia to 115 psia. So we stop when we reach 215. Good? Alright, we stop at 215. We assume constant entropy to calculate theoretical horsepower. And so we stop over there. Once we stop at 215, what do we read? 215. 215 is about that line. That line is 215. So when we stop at 215, we read two things. We read temperature. Okay? Temperature is this kind of line. So this is constant temperature line. So there's temperature line in Euler diagram. So 200 line is over there. 300 line is on the top. So we have 1, 2, 3, 4, 5 sections. This has to be 240 line. So we write almost 250, 240. So what we read is, number one, discharge temperature. Okay? After reading that, I got 230 Fahrenheit. That is the discharge temperature. The next thing to read is suction and discharge specific enthalpy, small h, specific enthalpy. So suction and discharge specific enthalpy is used to get the theoretical horsepower. That's come from, we look on the left side, we look over here on this scale, we get enthalpy, BTU per power mole, that is specific enthalpy. We look on that part and we get another BTU per power mole. So that is discharge specific enthalpy. And the bottom one is the suction specific enthalpy. That's why I say H1 and H2. Everyone got this? You have to do this in the exam for sure, right? It has to be in the exam, otherwise what do I test you? Okay, so we read H1 equal to 400, H2 equal to 1800. So in the exam, your number will be different, right? Can everyone read 400? Maybe you read 500, maybe 300 or something, but it has to be somewhere over there. Okay, it has to be between 0 and 1000. So if you get a big chart, you get this chart, right? So you don't know for sure, but it's somewhere over there. You may say 500 or something. It's also correct. So once we know a specific enthalpy of the inlet, suction side of the compressor and the discharge side of the compressor, then we get the difference. Okay, H2 minus H1. This part is about how to get do the conversion from flow rate million standard cubic foot to pound mole. Okay, what I did is, okay, standard condition they use 60 F, so it's 520 Röntgen. And R constant, there are several values of R constant, but I select that so that the unit become consistent. Use PV equal to nRT, and then N, number of mole, is P, which is that. Volume is 1 million, right, over R and over T. So that is standard pressure, standard temperature. So based on this calculation, 1 million standard cubic foot equal to that much per mole. Okay? If you happen to use, instead of 10.73, you use some other number, you may not get per mole, you may get kilogram mole or something else. But we use that, so we get per mole. So 1 million standard cubic foot per day is that much per mole per day. Agree? Like it? Alright. Then the difference, 1800 is H2, small h2, 400 is small h1. Suction side specific enthalpy and discharge side specific enthalpy, we got the difference then. So the unit of enthalpy is, from the chart is BTU per pound mole. When we have that number, which is pound mole per day. Pound mole per day multiplied by BTU per pound mole, we get BTU per day. That is the amount of heat in BTU per day. Got it? That's BTU per day. Okay, we want to ask that. Next, Alex we already talked. What's your name? Christian with a K or?
Yeah.
Okay. Alright, Christian with a K. BTU per day. That is the compression work. What is that unit in SI? Equivalent unit of BTU per day in SI is? Okay, next, what's your name, sir? Mr. Stark?
Yes.
Okay, Mr. Stark, what is the equivalent unit in SI for which BTU per day?
Watts.
Correct. It's watt. Okay. Watt is the unit of power. Power is energy per time. BTU is energy, there is time. So energy per time is unit of power. Unit of power can be in watt. Okay. And it can be pound force foot per second. Pound force multiplied by foot become work, right? Force with length become work. Work over time is energy, power. So this pound force foot per second is the unit of power. Okay, so 550 of pound force foot per second equal to 1 horsepower. 1 BTU is 778 pound force foot. So this is just a unit conversion. I have BTU per day. Okay. I multiply by that much to convert from BTU per day to be pound force foot per day. Good. I divided by that number to convert from pound force foot per day to be pound force foot per second. And I know that every pound force foot per second, every 550 of pound force foot per second is 1 horsepower that I That's why I divided by 550. Then I get 60.5 horsepower. That is theoretical horsepower. Okay, so next at the back, what's your name, sir? Ben? Colton? Actual horsepower and theoretical horsepower, which one is more?
Actual horsepower would be more.
Why is that?
Because you got some losses, heat, and you don't have 100% efficiency, just all that stuff.
Okay.
It's not constant entropy, that's why.
Oh, you know everything. Okay, that we are not operate at constant entropy. The process is irreversible. So S is not going to be constant. Okay, so we cannot just go up. It's going to be hotter than that if we need the same thing, and the efficiency is not 100%. All right. So is this number useful? What is that number has to do anything with us? Is that for sizing the compressor? Okay. You already know how compressor look like, right? When you drive to Midland and come back, you see several compressors. Yesterday I saw that, several compressors. So to buy any of that, we need to tell how much is the horsepower we need. This is a quick way to estimate it. Or if the vendor try to sell you, hey, you need about 100 horsepower, then you can double check it. Do some kind of quick calculation. Maybe the right answer maybe is 60.5, your calculation maybe 55, 60, 70 or something, but you know that what they tell you is wrong. It's not like whatever vendor tell you is correct, see? Like whatever I teach you, it doesn't mean it's correct. Sometimes modified by something that is nonsense, is wrong. It could be wrong. So you double check it. Alright, this is theoretical horsepower. The temperature 230, read from the graph. Okay. Compression ratio has two parts. Total compression ratio or compression ratio per stage. Okay. For this case, we calculate total compression ratio. We use this chart at the last stage divided by the suction at the first stage. Then we get compression ratio of 3.3. Who haven't signed the sign-up sheet? Everyone signed it? Great. Compression ratio per stage. Okay. Or if we have more than 4, if that number becomes 4 or 5 or something, we need total compression ratio more than a certain number, maybe about 4 or 5, we will need multiple stage. Okay, let's talk about that. Compression ratio, as you know, if compression ratio go up, volumetric efficiency go down. Okay?